Hey everyone, welcome to this explainer. If you're a CISSP candidate currently gearing up for the exam, you are in the exact right place. Today, we're undertaking a highly structured, rigorous instructional breakdown of some of the most critical topics you're going to face across domains 3, 7, and 8. We're talking all about malware and application security. I am so excited to guide you through this material because understanding exactly how these threats operate, and more importantly, how to defend against them, is absolute table stakes for any security professional.
Okay, let's dive right into this. Here is our syllabus for this explainer, mapping these threats directly to your CISSP exam mindset requirements. We'll start with malware and exam fundamentals, then look at ransomware and its legal thresholds. From there, we'll cover state and application exploits, break down web and injection vulnerabilities, and finally, wrap the whole thing up by implementing application controls.
Let's jump right into Section 1, Malware and Exam Fundamentals. Understanding the source and the evolution of malicious code is entirely foundational for anyone working in security operations.
First up, let's talk about who is actually writing this code. The CISSP exam heavily tests your ability to distinguish between distinct threat profiles, their motivations, and their key characteristics. Back in the early days, malware was mostly written by experimenters, just messing around. But today, it's a whole different ballgame. Consider script kiddies at the top. These are amateurs driven by curiosity or malice, relying mostly on pre-built tools. Contrast that with organized crime syndicates in the middle, who are motivated purely by financial theft. Think of the infamous Zeus Trojan that was used to harvest banking passwords. And finally, at the bottom, we have Advanced Persistent Threats, or APTs. These are your highly funded nation-state or military groups that utilize zero-day exploits and conduct incredibly targeted attacks. Knowing the stark difference in funding and motivation between an opportunistic script kiddie and a nation-state APT is absolutely crucial for your risk assessments.
Now, let's rapidly define the core malware categories you're going to face on the exam. We've got viruses, worms, logic bombs, and Trojan horses. Pay special attention here, guys. A computer virus actually requires some kind of human action, like a user sharing an infected file or clicking a bad link, to propagate and execute its payload. A worm, on the other hand, is completely self-propagating. It travels across networks entirely under its own power without any human intervention at all. Then we have logic bombs. These just lie dormant in a system until they're triggered by a specific condition, like a certain date rolling around or maybe an employee termination. And finally, Trojan horses, which maintain a totally benevolent appearance, like, say, a fake antivirus update, to hide a malicious payload inside.
But here is a crucial CISSP exam mindset note for you. In the real world, and this is heavily tested in scenario questions, these categories have very, very blurry lines. Modern threats often combine characteristics of viruses, worms, and Trojans all at the exact same time. So don't get boxed in by rigid textbook definitions. If an exam scenario describes a remote access Trojan or a rat that also acts as a node in a botnet and spreads like a worm, well, recognize that attackers are using blended approaches to maximize their impact.
All right, let's move to Section 2, Ransomware and Legal Thresholds. This area has seen a massive surge recently, and it creates some truly severe ethical and legal dilemmas for enterprise management.
So, ransomware weaponizes cryptography by encrypting your critical files and then demanding payment for the decryption key. But it is not just an IT problem. Read this quote from the U.S. Treasury Department. Companies that facilitate ransomware payments not only encourage future ransomware payment demands, but also may risk violating OFAC regulations. And this brilliantly illustrates the real-world stakes here. Many ransomware authors are actually subject to economic sanctions. This means that simply paying a ransom might cross the legal threshold into violating federal law.
Which brings us to a critical, overarching question. Should an organization actually pay the ransom? I want you to put on your CISSP manager hat for a second. You have to balance the desperate need to restore your critical business operations against the strict legal due diligence required when dealing with sanctioned threat actors. Honestly, it's a lose-lose situation if you aren't prepared. This is exactly why strong backup, recovery, and incident response programs are your only true defense.
Let's move into our third domain, state and application exploits. Here, we're shifting gears into software development security and exploring how attackers exploit predictable computer execution and, frankly, just poor coding practices.
There are three major threat vectors I want to detail here. First, Stuxnet. This was an absolute paradigm-shifting worm that actually caused physical destruction to Siemens centrifuges in Iran.
It literally marked the evolution of malware being used to cause physical damage and act as a weapon of warfare. Next, we have buffer overflows. These happen when an application receives input that is way too large for its allocated memory, causing data to spill over and corrupt other memory spaces. That often allows attackers to execute shell commands right on the system. And third, privilege escalation. This is where attackers gain a standard user foothold and then use tools, like rootkits, to escalate themselves all the way up to administrative or root access.
Now let's break down a complex concept that sounds like a bit of a tongue twister. Time of check to time of use, or TOCTO. Computers excel at predictable, repeatable tasks, right? Well, this predictability gives attackers a tiny, split-second window of opportunity. TOCTO is what we call a race condition state attack. It happens when an attacker alters an object, like a data file, between the exact time the system checks its status to authorize it and the time it actually accesses the object to use it. By literally racing the system and swapping the file in that millisecond, the attacker circumvents the authorization check entirely.
Here is another highly testable CISSP exam mindset note. While buffer overflows sound like deeply technical operating system issues, and they are inherently caused by developers failing to perform simple bounds checking on user input variables. The root cause, and therefore the primary mitigation you should be looking for on the exam, always points back to developer input validation. If programmers don't explicitly limit the size and type of input a variable accepts, a buffer overflow is pretty much inevitable.
Let's transition over to Section 4, Web and Injection Vulnerabilities. This is an area heavily tested on the exam, mostly due to the massive complexity and the very public-facing nature of modern web applications.
Often, web applications don't just hand over nice, readable database errors to attackers, so attackers have to fly blind. Let's walk through the step-by-step logic of a blind timing-based SQL injection. Step 1. The attacker injects a database command like wait for delay, basically telling the database to wait 15 seconds. Step 2. They monitor the application's response time. If the web page takes exactly 15 seconds to load, boom, the vulnerability is confirmed. Step 3. They iteratively test character values based on those forced delays. It's like playing 20 questions with the server. By asking the database true or false questions like, is the first letter of the password A, and telling it to delay only if true, an attacker can extract a database password letter by letter, purely by measuring how long the server takes to respond. Crazy, right?
Now, what's really interesting about this next concept is how simple it is. Let's trace the path of a directory traversal attack targeting a Linux password file. Look at the directory structure. If a web server's root is in the var/www/html folder, it absolutely shouldn't be able to access the etc folder. But if the server is misconfigured, an attacker can use the // operator in the URL to navigate up and out of that web root. By injecting // multiple times, they basically walk up the directory tree to the root, and then right back down into the etc directory to access restricted operating system files, like the shadow password file.
Okay, you absolutely must know the core distinction between these two concepts for the exam. On the top row, we have cross-site scripting, or XSS. This involves injecting malicious HTML or JavaScript code into a web page. XSS exploits a user's trust in a website, meaning the malicious code actually runs in the victim's browser. On the bottom row, we have cross-site request forgery, or CSRF. This involves forged commands sent directly to a server. CSRF exploits a website's trust in an authenticated user's session. It essentially piggybacks on their active login to make the server think you authorized a malicious action, like transferring funds out of your bank account.
Take a look at what a stored XSS attack actually looks like in practice. Here, malicious code was permanently saved on a message board. When an unsuspecting user views the post, their browser just automatically executes the code, creating this alert pop-up. Now, a pop-up is just annoying, right? But a real attacker wouldn't be so visible. They would use this injected script to silently steal your session cookies or redirect your browser to a malicious phishing site entirely in the background.
Let's look at another CISSP exam mindset note, this time regarding Insecure Direct Object Reference, or IDOR. This happens when an application relies on simple URL parameters, like maybe an account ID number, to retrieve records without ever actually checking if the user is authorized to view them. A Canadian teenager was famously arrested for simply altering a URL integer by one single digit to view other people's private government records. Keep in mind, IDOR is a severe authorization failure. Altering a simple URL parameter to access unapproved data completely crosses legal thresholds and can definitely be classified as unauthorized computer use.
And we have reached our final section, implementing application controls. Here we are focusing entirely on the defensive countermeasures and the strict due diligence requirements expected of a security professional.
So how do we actually stop these application attacks? Well, the absolute gold standard of input validation is input whitelisting, which you might also hear called allow listing. This is a strict validation control where the developer defines the exact specific type of acceptable input, like requiring exactly 10 digits for a phone number, no dashes, no letters, and rejects literally everything else. But attackers are clever. We have to contrast this with attacks like parameter pollution. This is an attack that tries to bypass those filters by sending a web application more than one value for the exact same input variable in the URL. If the web platform fails to handle duplicate variables securely, it might inspect the first one, say, looks good, but then accidentally execute the malicious second one.
Please literally commit this next CISSP exam mindset note to memory. Client-side input validation is never a security control. Validating input in the user's web browser is great for a snappy user experience, sure, but it can be trivially bypassed by any penetration tester using a simple local proxy. All security validation absolutely must be performed server-side to prevent tampering.
Because prevention isn't perfect, we desperately need database defense in depth. Here are your essential due diligence controls. First, data minimization. Simply don't collect or keep sensitive information you don't absolutely need. If you don't have it, they can't steal it. Second, tokenization. Replacing sensitive identifiers with a unique identifier via a secure lookup table. Third, hashing. An irreversible cryptographic replacement of data. And finally, web application firewalls, or WAFs. These sit right in front of the web server to perform Layer 7 filtering. These layers of obfuscation and application firewalls protect your data even if that outer perimeter is completely breached.
Let's look at how developers should actually write their database queries to stop SQL injection cold. Consider the difference between parameterized queries, where the developer prepares an SQL statement but strictly defines user input as variables, versus stored procedures, which are precompiled SQL code stored directly on the database server itself. So the crucial point for the exam is this. Both of these are primary, highly effective defenses against SQL injection. Why? Because they both strictly separate user input from the executable code, making it totally impossible for an attacker's injected text to accidentally be run as a command.
We're going to wrap up with a pretty critical question for you to take back to your teams. With attackers constantly utilizing fileless malware that lives purely in memory and unleashing zero-day exploits left and right, is your organization's defense-in-depth strategy relying way too heavily on outdated, signature-based antivirus? I challenge you to evaluate your own environments today and start thinking beyond simple antivirus to a holistic, layered application security model. Thank you so much for joining me in this explainer, and seriously, good luck on your CSSP journey. You've got this.